I hope you remember from your past that the compound interest formula is often written as A equals P times 1 plus R over N to the N times T power, where P is called the principal, spelled AL at the end, not LE. That's the amount of money that you deposit. Right now, say, time 0. T is the time, most typically written in years. R is the nominal annual interest rate. And if it's, for example, 4%, percent means per 100, 4% really means 4 divided by 100. It would be 0.04 in that case. It's called nominal because that means a name only. When it's compounded a certain number of times per year, like n times per year, you actually earn a little bit more interest. It's to your benefit when you have a savings account. N is the number of compounding periods per year. A is the final amount at the end of the time. You could call it amount. You could call it balance. In fact, we're going to use the letter B here in a minute instead of A. B for balance. I'm just reminding you of the compound interest formula here. This is actually not our main concern. Our main concern is thinking, first of all, about this equation in a different way, using, instead of a nominal annual interest rate, a continuous interest rate, as if you're getting money every second of every day. Boom, 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 boom. Right? With today's terrible savings accounts rates, although they're doing better, on $100 during a whole year, you might earn 1 or 2 cents of interest. So you're earning tiny fractions of a cent every second of every day if you're doing continuous interest. Usually with banks, N is 4 or 12. 4 would be every 3 months, quarterly. 12 would be monthly. But the corresponding continuous formula involves the number E. And let me use B instead of A, because that's what the book does. I still will use a P, and I'll still use an R for the interest rate, but it's going to be a continuous interest rate in this case. So P is once again the principal, or I'm also going to change my perspective. I'm going to call this something different now. I'm going to call it a present value. T is still the time in years. And when you use E like this, I hope you remember from either pre-calculus or calculus 1 that that's called a continuous annual interest rate. It's somehow reflecting the fact, without being real specific, real precise here, that somehow you're getting interest every second of every day, even every millisecond. Right? That only amounts to ordinary amounts like pennies or even dollars if you've got millions or billions of dollars in the bank account, which you would not want to put $1 billion in one bank account. That would be a bad idea. Even if you had $1 billion. What's B? You could call it balance, B for balance, and that might be why the book called it B, but I'm going to call it the future value. Present value and future value are more general ideas than, hey, here's my principal, what I deposited, and hey, here's my amount at the end of the time that I leave the money in the bank. The ideas of present value and future value are more general ideas. I don't want to get into exactly how they are different, but we'll still think about bank accounts. I do want to change the terminology here. Why use a continuous interest rate instead of an actual nominal interest rate? For one thing, it's because this is easier to differentiate. It's also easier to integrate. That's why. You can always convert from one to the other. That's always possible. And maybe you even remember doing such conversions in pre-calc or calc 1. Maybe you've forgotten how to do them. But it can be done. And yes, in this form, it's easier to differentiate and integrate. That's why we like it. It is worth emphasizing that you can think of that equation in an equivalent way. You can solve for P in terms of B instead. This is the future value in terms of the present value. I can solve for P, the present value, in terms of the future value by doing what? By dividing both sides by e to the RT. That's what. Same as multiplying both sides by e to the negative RT. I can write P equals B e to the negative RT power. And yes, this equation can be used for specific bank accounts. Let's imagine doing a couple examples. For example, I might wonder if I deposit $1,000 right now, if P is 1,000, in a bank earning, wow, 8% interest for 10 years, how much is that money going to grow to? I'm using this first equation here to do this. It's going to grow to 1,000 times E to the 0.08 times 10 is 0.8 power. I'll type it in as 0.08 times 10. It grows. It's bigger than 1,000. $2,225.54. That's how much $1,000 will grow to at a continuous 8% annual interest rate for 10 years. Are you really getting pennies every second? Well, it's really fractions of pennies again. All right, that's the future value after 10 years of $1,000 now. Conversely, you could ask, what's the present value of $1,000 right now? 10 years from $1,000 being given to you in the future. Kind of a weird way to think about it. Another way to think about that is, how much should I deposit right now to get $1,000 10 years in the future? I'd have to do this calculation. And that'll be less than $1,000. 1,000 times E to the negative 0.08 times 10 is $449.33. That's how much I need to deposit right now to have it grow to 1,000 after 10 years. So that's a couple basic problems, but we want to do something a bit more complicated. We want to not just think about discrete deposits, but also continuous deposits. You could call them income streams. Income stream. Or you also could call it a payment stream. That's a function of time, and whose units could be dollars per year. And let's go ahead and dream big and imagine Elon Musk hears about you and really likes you. In the first section, it was your uncle. Elon Musk gets to know you and really likes you, and Elon Musk says, I like you so much, I'm gonna deposit $1 billion in your bank account every year for 10 years. At all moments in time, every second of every day. Not $1 billion every second of every day, but averaging out to $1 billion per year. How many dollars per second would that be? You got to figure out the number of seconds in a year. There's how many seconds are in an hour. Here's how many seconds are in a day. If you include leap years, here's how many seconds are in a year. 31.5576 million. Take 1 billion and divide by that, it amounts to $31.69 every second of every day for 10 years. Will give you $10 billion over 10 years. But what are you going to do with that money? That money's going into your bank account. your bank account is earning interest. You're going to have more than $10 billion after 10 years. You're earning interest on every little chunk of money that comes into your bank account every second of every day. How much will it grow to overall? What's the future value of the entire income stream? Maybe it's helpful to draw a number line, a timeline from 0 to 10 years. And let's think about a small amount of money that comes into your bank at time t over a small amount of time of length delta t. The small amount of money, the small amount of principal, you might call it, delta p, that comes into your bank during that small amount of time, delta t, should be P, approximately in general, P of t times delta t, where P of t may not be a constant function in general. For our example, it is a constant function. In dollars per year, it's $1 billion per year. So this would be 1 billion times delta t. Delta t is a small amount of time. If it were in seconds, it'd be 1 over 31557,600. 3 times 10 to the negative 8 years would be 1 second. You'd multiply that by 1 billion. To get that $31.69 during that second. That's the small amount of money that comes into your account at the small amount of time. How much will that tiny amount of money grow to after the end? You need to use this formula, but not growing by t more years, instead growing by 10 minus t more years. And you do that for every small chunk of money over the small chunks of time, you get the total growth in all the money. The balance of such a small amount would be the small amount itself times e to the r times not t, but 10 minus t. The final balance would be the sum of those small balances, a sum like this, and then also use the fact that delta p is 1 billion times delta t to write this as, in the end, 1 billion, which is 10 to the 9th, times e to the r times 10 minus t, delta t. That would be an approximation for your final future value of the entire income stream. Let delta t go to 0, you get an integral. That gives you the exact future value. What would that integral be? It'd be the integral over the entire time, 0 to 10, of 1 billion times e to the rt, if r is 0.08. I plug that in, not RT, but R times 10 minus T. You do have to do 10 minus T there, not T. Which means if you're going to do that integral by hand, it's a little tricky. You'd still need a 10 minus T up there. If you want to be careful, you could do a substitution, W equals 10 minus T. But then dW would be negative dt. It'd be a little tricky. What should we get? We should get something bigger than 10 billion. Over those 10 years, Elon Musk gave you $10 billion, but you put it in the bank account, and so it's growing all the time. It's got to be more than 10 billion. It's about 15.3 billion. 1.53 is times 10 to the 10th is about 15.3 billion. That's what the future value is. It grew. You could also, last thing to do today, turn it around and say, you know, Elon, I'm really happy that you're giving me $1 billion a year every second of every day by giving me $31.69 every second of every day. But I'd prefer if you gave it to me all at once. Give me my money now as a lump sum. Please, you can do it. You can afford it. After all, you bought Twitter for $50 billion. Oh, sorry, X. Give me my money now. How much should he give you now at time zero so that its value would be the same as the entire income stream if you took that money and put it in the bank account right away and let it grow for 10 years? You'd have the same amount of money at the end. That would be a present value. You'd think about it in the same kind of way, except the small amount of money would not go forward in time by 10 minus t years, but come back to the present by t years to time zero. And you also would need a negative r instead of a positive r because of this equation here. So you would get, if you did that, here's what you would get. Integral from 0 to 10 of 1 billion times e to the negative 0.08 times t, not 10 minus t. You'll see these formulas in the book. It's got to be less than 10 billion. Yes, it's 6.9 billion. Will that really grow to the same amount of money? Yep, it does. Multiply by e to the 0.08 times 10. That lump sum at time zero, growing for 10 more years by itself, comes to the same final future value at time 10. In general, you should also be able to handle payment streams that are not constant functions, but might have some formula involving t. So maybe it equals t. So you're getting money faster and faster over time. The same kind of ideas still work. All right, have a good day.